Ready whenever you are.
Okay, we're live on YouTube.
I put my bike on the train and I bike off. And when I saw that I had to fill, I just logged my bike up and
Welcome to the AI infrastructure race. Hello, welcome to AGI. And it is a joy to be celebrating the creation of gigawatt scale data centers. There was a sense, Alex Krasevsky working on a GPU in, his room, thinking through how to more efficiently set up this concept. That this was going to be a local phenomenon. But we now live in an era where a huge fraction of the world's compute is being devoted to this core idea, the idea that scaling compute is the center of how we end up creating superintelligence. My name is Jeremy. Welcome to AGI House. Here we believe there's a spirit to Silicon Valley. In my mind, the concept of the amount of compute and data required in order to execute on training the next generation of general intelligences being so massive is a core idea to the spirit of Silicon Valley. That is, we are very opportunistic people. We think huge, we think out of the box, and we execute on what has been really a glorious season of basically bringing into what I would like to call the intelligence age. So first of all, welcome to AGI House. You're on the third story of this 4-story mansion with a glorious view of the entirety of San Francisco. Hopefully you have some sense that the totality of the invention and creativity that exists in the city can be viewed from where you stand right now. You do stand in part in the shoes of Chris. So the origin story of AGI House is where Andre Karpathy, myself, Arvind Srinivasan, this is back in September 2022, before the launch of ChatGPT, we're co-creating with incredible technologies like the ones that we're describing today. And this crew went on to create multiple unicorns, and in fact, the space in which you sit is sort of inspired by their inventions. In many ways, I see Silicon Valley as special. And one of the ways in which it's special is computation. That is, we have this way in which we take mathematics seriously by basically issuing a generation of computational systems, new kinds of mathematics that are capable of things that every civilization past was not capable of. And so, in part, is in that tradition that I hope we can reify the future of computation and the future of data and data infrastructure here. I will first request we have a huge round of applause for the creator of this event, Margarita. Margarita is fully responsible for the suite of speakers you're about to see. You'll hear from SF Compute, you'll hear from Cerebras. We have a number of phenomenal thinkers when it comes to creating new data centers here. So let's hand it off to Margarita.
Hey guys, welcome. I'm Margarita, CEO of AirVolta. Let me pull my laptop for a second. So today we're going to have some super exciting speakers. We decided to put together this event because we want to bring together our friends, our partners, and companies across the data center space in San Francisco. I think San Francisco talks a lot about ML and applications and LLMs, but the actual watts and bits and electricity that makes it all happen, we don't talk about as much. What we do at AirVolta is data center management. So how do these behemoth structures actually work? You have the networking components, the electrical components, the building components, and all these management systems. In the past, what we've done is build tooling for devices like this. It's been a long 20 years of, the typical data center being 1 megawatt, maybe even 500 kilowatts. And now we're getting to 1 gigawatt level structure all throughout Texas and everywhere else. And so we've updated our tooling in order to support these types of structures. And that's what AirVolta does. What you'll hear from today is a variety of speakers from the energy, from the chip development who are building their own data centers, to the actual co-locations, the hyperscaler developers, and then the folks that sell it all. So I'll introduce the speakers in a second, but we kind of come here as just a conversation. Each speaker will have 5 to 10 minutes to present their topic, and then we'll jump into Q&A. So definitely think of questions or whatever you're curious about. and then we'll have a couple of minutes per Q&A per speaker, and then afterwards we'll all just do pizza and chit chat about what we heard. Sound good?
Yep.
Cool. So let me introduce the speakers. Let me just pull it up. So first off, we'll have Asher from Cerebras. He'll be coming up in just a second. So he'll be telling us some exciting stuff about Sovereign AI and what Cerebras is doing over there. We'll also have Xander from Kratos. We'll have Marilyn Miller from Vantage Data Centers. We'll have Honors Masters. We'll have Ryan Cunningham and Evan Conrad. So I'll call you guys up in the order you're gonna go. I think we're missing one more person, so I'm gonna have to switch up that order a little bit. Oh, there he is, he just came. So, yeah, I'll call you guys up, but first up, Asher.
Hi everyone. I usually just start off by showing like what we really do at Cerebras, right? So we also do training, but this is kind of what we're building here, for what it looks like for actual people. So here's a video. On the left is going to be a Cerebras doing Llama 4 Maverick, and on the right is going to be a GPU. And this is really the difference here for the same problem. Except that's lagging. Okay. It'll happen. So you can see the Cerebras finish this. And so for all you guys that do code generation out there who like code, this is kind of what you're waiting for. This is like the time that you go and you get distracted and you go get water. So maybe get coffee. Okay, it finished. So the way we do it and the way that Cerebras is kind of like differentiated from pretty much every company in the world is that this is our chip. So this is the Cerebras chip. You can see the size of my head. It's actually the brain of the future of AI. So you can see here, this is the B200, it's the newer NVIDIA. It's around like kind of like two H1 200s put together. And this is the Cerebras chip. So it has around 900,000 compute cores, 44 gigabytes of on-chip memory. It's completely identical dies. It's the biggest possible chip you can make out of a TSMC wafer. And I'll pass this around after the presentation. But the reason that it's so big is because we're able to fit all the memory that you would have in the high bandwidth memory for a model on the silicon. So you can get rid of the memory bandwidth problem for a typical GPU, and that enables speeds like the video I showed before. But as we were talking about, this isn't a computer talk, this is about the data centers. And a big problem with these alternative chips is like what hyperscalers are going to buy an alternative chip, because they don't know if there's demand, they don't know who's going to buy it, everyone knows GPUs. So in order to actually get your foot off the ground and prove that we're the fastest, you have to build our own data centers. So that means we're building the chips and the computers and the racks that the computers go on and the actual data centers and the software for the chips for you to actually code the models. And then the inference cloud on top of that for you to run the API calls. So it's a completely verticalized stack and verticalized company. And the building out the data centers has been a lot of fun. So this is an image from a data center out in Minneapolis. And this was co-built by G42, which is a company out in the United Arab Emirates that's like their AI national champion. And with them, we're working on sovereign initiatives to get inference compute out into the world, partly for the government there, and partly for our personal usage and our customers. And so that's an example of what I'd call sovereign AI, where a country wants to develop a data center so that it can retain its national data. It can make national large language models on top of that data and actually retain what we call sovereignty. Like, this is our ownership. If we are at war with a certain country, we don't have to worry about our AI being pegged on one country or another. So this is something that we built. This is our newest data center built last week in Oklahoma. And you can see it has 60 exaflops of compute in that data center. It's massive. Hundreds of these wafers inside of computers, inside of this data center. A funny thing is also tornado resistant, so it can withstand the largest tornado ever recorded in American history, and as well as earthquakes. So it's a pretty cool thing. I mean, we have the world's best data infrastructure put up there. It's not just marketing. For some people it is, I guess. And that's going to power all of the amazing businesses out in Oklahoma, as well as throughout the country. So this is kind of an inside look what's going on in the data center. You have these racks. This is for water cooling here. So you attach the power, you have the Ethernet cable going between the chips. And each chip has water cooling, where you actually have to water cool the dies individually. So you have the chip here, you have the motherboard there, and you have the cooling shooting water using really interesting physics to each die to cool it down. And this is the only way to cool down this massive chip, because you can't do this in a normal computer. You need the water cooling. So a lot of physicists have worked a long time to try to make this possible, and it's cool to see it come to reality and everything else. So the last thing I wanted to talk about in this short talk is about sovereign AI, I was discussing before. So my main role is I'm actually working with different countries to develop sovereign compute in countries. So this is one that we did with Kazakhstan. It's a country in Central Asia, very sparsely populated, but huge country. And we developed the top-performing Kazakh large language model for many different parameter subsets. So this is just an 8 billion parameter Truecaller chat that we built. It can compete with the Kaz-LM, which is a competitor in the nation, but also with Clem 2.5, 7B, a lot of people want 8B. And we trained this from scratch. It's not a fine-tune. We took Kazakh data and we built a large language model with the company. And we've done this with Arabic. We're doing the top-performing Arabic model. We've done this with Indic languages in India. And we're trying to do this with a lot more countries all over the world to help them create their own national projects. So I'd love to answer any questions you have about how we're doing this, how we're going to different countries. We've done it in the UK. We're talking to many countries in South Asia, Southeast Asia, Africa, to see how can we create AI ecosystems there, national ecosystems that can serve the populations. Thank you.
So, any questions from the audience?
Yeah, I wonder if you could just talk about what are the biggest obstacles to your growth? What are the pain points that you're facing?
Yeah, so I think an interesting obstacle is it's very risky to choose a new architecture, right? So everyone knows GPUs and everyone knows they're going to work and they know that they're going to have the demands. And there's also a lot of people who can code in the CUDA language onto the GPUs. So one obstacle we're facing is how can we convince the foreign government to spend taxpayer money on a perhaps more risky asset, right? So you have to prove out a lot of other things that we can do for them besides just offer super fast training and inference. And for training, we can actually hit around, we could train a $1 trillion parameter model in a week using the chip. You can have it all go through the layers and the weight stream through one single chip. I mean, we'd use multiple chips, but there's some really cool advantages, but we'd have to do a lot of convincing because you're from another country, you want what everyone else has, right? You want the thing that you know works. So it's about risk tolerance. Yeah.
What's stopping NVIDIA from copying your chip design?
Oh, nothing, I guess. I mean, there's something.
So, what exactly is
I can be more specific. The Dojo, which is the Tesla, they also tried to make a wafer chip scale engine, and they canceled operation. A lot of companies have tried it. It's just they haven't figured out the technology. So it could be that NVIDIA doesn't think it's the best way to do it. It could be that they haven't done it, or they're not investing the resources. But from my understanding, it's a really cool technique that nobody's cracked yet. Yeah.
How do you justify the sort of cooling around this? Because the thing that I'm thinking about is, on the edges maybe it's okay, but in the very center, and given the density that you're working with, as Moore's law continues, obviously the density on each chip is going to be larger and larger. How are you going to sustain the cooling that's going to be able to power these chips for the future?
Yeah, it's a great question. I think with new additions of the Cerebrus chip, I can't give you details, but there are going to be differences in architecture that can enable that to happen. But I would say for now, the Blackwells are also water cooled in a similar way. So it's going to be the new standard of this water cooling. And I think all the data centers, like the next speakers are talking about data centers they're building, are naturally going to be water cooled. It's a great question. How much time?
We have a couple more minutes.
Okay.
So,
Yeah.
so it sounds like you are specifically not targeting the U.S. market. Is that
We're also targeting the US market.
okay.
Me specifically, yeah, we're not that big of a company, so we're doing everything.
Okay.
Yeah.
What's the PUE of your data center?
PoE.
PUE?
Power usage.
Oh, okay, I don't know.
If
the
you know
number.
that.
I think it was actually in the slides there, I could pull up.
Okay.
Sorry about that. Yeah,
What's the U of your, yeah.
well, it's a good question.
Yeah.
So I think the one thing that nobody mentioned yet, and I didn't mention either, is that like the chip itself is so big, so there's gonna be more errors, right, by probability, right?
Yeah.
Yeah.
So what we've managed to do within the Cerebrus chip is we managed to route around errors. So we
Okay.
have some reserve units so that if there's natural errors in the silicon, instead of just trashing the whole chip, we can route around it with the cluster software and actually develop new models and preserve the. But I would say that the rate at which the NVIDIA they drop is the same as NVIDIA. So the Cerebrus chips are like have a similar drop rate as normal chips in the market for yield. Yeah.
Sorry. I know that the issue a couple years ago was that you guys could do really fast inference on one chip, but then you had scale out issues, where the second that you had to go off chip to get something from memory, like somewhere else, your off chip networking was like not as good as your on chip memory bandwidth.
Yeah.
Have you managed to fix that issue? And
So I would say that the off chip is like 1.2 petabytes, right?
that
Yeah. So
Sure.
so the NVIDIA one is much quicker. It's much faster. But the theory is like because we do so much on chip, it actually this is the more important calculations are happening on chip. So we haven't seen an issue with inference speeds. Like this is with multiple chips. The video I showed you.
sure, but
So
you
we
were
haven't seen
showing
issues with inference chips between the chips.
sure, but you were showing like a 32 billion parameter model. Does it scale the same way with like a 576 billion or like?
Yeah, it
Okay.
should scale the same way. But I think it's something we're always going to have to work on.
Sure.
Yeah.
That's it for questions.
Thank you.
Thank
Thank
you
you.
so much.
Let me ask you this before.
Next we'll have Evan Conrad from SF Compute. He's going to talk to us about Optake. Let's give it a second here. If anyone needs the Wi-Fi, its attention is all you need. Always.
Does this work? It does. Okay, cool. Hi. So this talk was put together very quickly, so I'm going to apologize for that. My name is Evan. We make a company called San Francisco Compute. We help people get offtake. We make a compute market. Lots of people seem like they are making compute markets nowadays. This talk is a bit about why you would want a compute market in the first place, because I think it's not super obvious. My general asks, though I'll ask it for the rest of the talk, is that we're hiring, and so if you are a systems engineer, a Rust programmer, or you are interested in go-to-market or BD roles, or finance, you should join us. We're growing extremely quickly, and come talk to me, or Coursera, who's somewhere over there. Cool. So yeah, this is a talk about Optake. Just out of like show of hands, because this is Silicon Valley, but also this tech week, and so there's lots of new people coming in. Who knows what the word Optake means? Okay, great. More hands than normally in San Francisco. I'm just going to explain that. So an offtake agreement basically means somebody is buying your cluster from you. So when you finance something, a project, you typically want somebody to like buy that thing from you, so that way you don't just build the thing and then it sort of sits on your balance sheet and then disappears or like lights money on fire. It's really important that you have very good offtake. You have offtake that's from somebody with really low credit risk. But really what this means is just a long-term contract on the cluster that you've got. If you don't have this, you can't finance your data center, or you can't finance your cluster, or you can't finance whatever you're setting up. Offtake in GPUs is not a thing that people have typically thought about in cloud in the same way that we previously thought about it. And so I'm going to walk through how the economics of it work from a very high level. So this might be super obvious to some people and might be like new information to others. But here's the kind of problem of AI, is that the margins of GPUs never improve. Or, sorry, the margins of the application layers never improve. which also causes the same problem for the cloud providers. So in CPUs, you would set up some CPUs and you would sell to SaaS companies. This is like your Gusto or your Rippling, and they buy your CPUs, and then their revenue goes up, but their costs don't really go up, not at the same rate. Your Gusto or Rippling, you can close a bigger deal by just having your salesperson say the higher number. So your revenue can increase without your costs increasing. But if you're pressing generate, like that's what your application does, every time you press generate, you're spending more money on compute, which means that your margins are thin the whole way through. It like never gets better. There's a lot of people who sort of assume it never gets better, or assume it will get better, but it's just the bitter lesson. It's just scaling loss. It just never actually does get better because it doesn't work like SaaS. That causes a problem because if you're a cloud provider under the hood, no one cares at all about the software that you make. If you're buying your CPU from a CPU cloud, you care a lot about the software that you're working on. There's a reason why people go with AWS, not Hetzner, or just rack and stack themselves. But if you're a GPU buyer, then you have kind of two options. Do I spend $200 million on a managed service product, or do I spend $100 million in bare metal? So if I wanted the same margins that I would have gotten on CPUs with that same markup, then I might build a great software product. I would build cloud, I would buy a bunch of GPUs, and then I would expect a high markup on those GPUs, 50% markup or 100% markup, or something. And then I would buy $100 million in compute, and I would charge $200 million for my great software product, if I wanted the same profile as a CPU. And if anyone has ever tried selling GPUs, you will immediately learn that no one is ever going to do that, ever. Like, there's no product at all. It doesn't matter what your product does. Because your customer is like an AI lab or something, and that AI lab has raised, big giant fat VC check, and they're going to spend all of it on compute. They're $50 million pre-revenue, whatever, and $48 million is going to compute. And if you try to charge a markup on that, there's no more money in the bank account. It doesn't matter what the company does. So that means that your only value proposition when you're setting up clusters is how do you get the COGS down? Like, how do you make your hardware costs go down? Because then you can compete on price. And the function of COGS is you got a big fat chunk going to NVIDIA, or maybe Spheres. And then you've got your cost of capital. That's a cool lever you can play with. You got your cost of your power, your cost of land, maybe operational costs elsewhere. But your power and your land is also just cost of capital. Because if you were to, say, try and reduce your cost of power, you could buy a power plant. And if you had really cheap cost of capital, and lots of it, you could buy the power plant and get the whole thing cheaper. Same with the land. And so the problem with this is that if you make great software, if you make a product on top of the application layer, you make a platform as a service company, you make a great cloud provider that has all sorts of nice software, if you're in the business of making software, which is what most of Silicon Valley is, you're just never going to outcompete the UAE. You're never going to outcompete Brookfield. You're never going to outcompete these massive funds that are deploying capital at wild scale. And there's just nobody who's got cheaper cost of capital if you just already have $100 billion to spend and it's your money. You're just never going to win. And so your only option if you have great software is to rent. There's somebody else who's going to deploy the cluster. They're going to be the one who owns it because they have cheap cost of capital, they have the access to power, they have the access to land. And you, as building a great software application, either an application company or a platform as a service or whatever, you're going to need to rent. And then if you own the hardware, so you are the person deploying the capital, or you are the person setting up the cluster, or involved there, your only option is really to sell a long-term contract. Because your customer does not care about the software at all. They're not going to value it in any capacity whatsoever. And because of that, all the other people are not valuing it, which means you need to offer the lowest level access to the hardware. And you pretty much need to sell bare metal. And you need to sell it for a long-term contract, an offtake agreement, that is at a reasonably low margin so that way you can compete on cost. That causes a problem. Specifically this problem, which is if you're buying compute, if you're an application layer company, your incentive is to buy for as short a period as possible. Because if you don't, you'll go bankrupt. If you buy a really long contract from someone, and now your margins are thin, and suddenly your demand is not what you expected, then you will go bankrupt. This is where the bubble is. If you're worried about where the bubble is, it is because there are countless startups or countless companies right now who are buying long-term offtake agreements on clusters, and then they are selling short-term demand, short-term usage to their customers. They're basically WeWork.
like all the application layer companies are WeWork. They have net 30 billing, they charge monthly, and they sign up for 3 years on a long-term contract. So if the demand does not go up, then the whole thing blows up, which is not super great. And the problem with that is it's not just like a bet on the demand going up. It's also a bet on your margins somehow improving from nowhere, even though you've locked out in your contract. It's a bet that your usage isn't or like stays consistent, even through night and day cycles. But meanwhile, like you're never going to set up the clusters. You're never going to get the clusters financed in the first place if you don't give the underlying like cluster owner a long-term contract. If you don't give them secure offtake. So basically, if you're buying for peak on your inference load, you might overspend, and then maybe your margins go away. Or if you're buying for base, then you underspend, and then you don't satisfy your SLA, which means your customers disappear, and they go to whoever else who is taking the more risky option of buying for peak, even though that person might be in the bubble and is purely funding on venture capital. Our take at San Francisco Compute is you cannot get secure offtake. You can't get the thing you need to finance clusters if you don't have liquidity. There is no market in the world that is going to support this unless you have liquidity, unless you are able to sign a long-term contract with someone that you can exit, that you can get out of by selling it to somebody else. This is what compute markets do. They are not like an Uber for X, they're a market for offtake. This is how the power markets work to some capacity, but not exactly. It's like actual people in the room who know a lot better. But this is how it actually needs to work. You need to be able to finance your cluster against an offtake agreement that can exit. Because if you're financing your cluster against an offtake agreement with somebody who is just an application layer company who may or may not have the demand, then that's a bubble. That's something that's going to blow up the economy. So that's what we're doing. We're building the offtake machine. We're building a market for GPU offtake. We're growing very quickly. If you are looking for a job, we would love to have you and love to talk to you. That's pretty much it. We're kind of a very low-key company. Yeah, cool.
Question?
Are you guys doing the offtake off of your own balance sheet, or are you allowing other people to do the offtake?
When we do it, we get all the cash up front, and then we give it to somebody else. So basically, it is from our balance sheet, but we secure the risk by having cash up front.
Okay.
So we have specific contracts too that like make it so that when particular failure cases happen, like for example the cluster ends, it's not from us. So we've designed them so that we're not the thing that blows up. Very important.
Yeah, how did you come up with this concept? Because usually when I hear offtake, it's like natural resources, right? Like when I heard about it, it's like lithium mining and doing offtake, contracts. How did you come up with it for data centers?
So we definitely didn't come up with the concept of offtake for data centers, though we came up with San Francisco Compute because we got trapped. So I used to run the Anagrant first batch, and then after that, I started a company that was basically an audio model company. It was kind of like pre-Sonora UDO. It was basically Sonora UDO before that. When you did that, you had to buy an offtake agreement. You had to buy a long-term contract from somebody, and they would take that contract and use that to finance the cluster. We could not afford it because I had raised $500K, which is a very small amount of money to use, or in AI, I guess. And the thing we could afford is to go with someone who didn't look at our bank account, and then we could buy 12 months, paid month to month, and we could afford exactly 1 month, and then we would sublease the other 11 months to somebody else, and that's how we would get our cluster. Unfortunately, when you do that, you immediately go bankrupt every month if you don't sell out your next month, which we learned in about 30 days. Would not recommend it. So then we were in the business of selling that cluster every month, and we became really good at selling that cluster every month. That led us to create a literal order book for selling other people's GPU clusters, because people would come to our website and ask us for more GPUs than we actually had, which meant we would turn around to somebody else and say, hey, do you want this contract? We'll split it up for you. And we became GPU market makers. That ended up developing into what is SF Compute today, which is a literal order book for GPU offtake.
Could you talk about some of your customer profiles, if that's okay?
There's customers on our website, but in GPUs, many people are very private. The thing I can say is that we work with some products you have probably used, but we don't have the, we signed NDAs and not allowed to talk about them.
Right.
The other thing is that as part of SF Compute, we are very hesitant to appear as competitive to the underlying clouds that we work with, but we work with 11 different clouds, and we do thousands and thousands of GPUs. We're bigger than some GPU cluster or GPU company, or like entities is cluster. I don't like saying the word neocloud. It's kind of like a weird, I think it gives the wrong impression. I've been using the word MCP because it's the word NVIDIA uses too much, and that's probably the wrong language. But we're bigger than some and not bigger than others. It's going to be the description.
So would you consider yourself going in the direction of being known as an AI hyperscaler? So like a CoreWeave, like a Lambda Lab, like how, I'm trying to understand what the differentiating
We're trying to
are.
be the grid for GPUs. We don't think any of this works like cloud at all. We don't think it works like hyperscalers. We think that hyperscalers are mostly going to start to buy GPUs from folks that look closer to like Brookfield or something. And they will layer on their own software stack. And our general impression is that they're going to buy from a market that they can sell back on, because if they don't, they will go bankrupt. So we've just taken a very strong bet that everyone who doesn't work with us or work with a market in some capacity is just going to go bankrupt. So you can make really strong bets when you do that.
I really like the idea. I was wondering, like, when you think about commoditizing compute, how are you standardizing like an agent?
At the moment, we have an order book that has a lot of constraints on it. So you can say, first, it has a concept of co-location on the same RDMA fabric. So you can say, oh, all these nodes within the same cluster. And then it has things like storage and network and various types of SKUs. The other things we do is we just like only allow certain things onto the market and then price them differently. What we're trying to get to, and we're working with vendors to, is create like SF Compute spec, which is something that you can build against, and you can finance against that. But that will take a bit.
Yeah. How long are the offtake agreements, and how many of them are single customer versus like agglomeration of customers making up an offtake agreement?
So at the moment, the longest we've had is 2 years. That one was a single customer, but the caveat to that is the thing that happens when you make a market for compute is somebody buys a contract, and that's like the initial seed. But then if they sell back liquidity from it, it's technically it's like a conglomeration of a bunch of people. But importantly, if you have the first person pay up front, or you have another person's taking on the credit risk for it, and then the underlying owner is already paid up front. So a little bit more complex than that. This would be easier on the whiteboard.
You said you're something like a market maker for GPU compute, but you also said you have the customer lined up and then you go and offtake. Now, my question is, why don't is there a way your customers go around you and just go offtake themselves because they know what they need, and so they go around you?
So the reason why someone works with us on a customer, like from a demand side perspective, is they can sell back. If they went directly to say CoreWeave, they would not be able to sell back. But if they went directly through us and then worked with us with CoreWeave under the hood, then they would be able to sell back, say, 30 to 40% of their capacity that is not used at night or weekends. And that's a default 30 to 40% discount.
Okay.
That's why. So people typically bring us to the data center.
Okay, so next we're going to have Ryan Cunningham. Ryan is an expert in energy, compute. I think you guys will enjoy it.
Thank you, Margarita. I would not describe myself as an expert in the least, but we'll do what we can here. Where's the Asian market? All right, cool. Hello, everyone. My name is Ryan Cunningham. I am the founder of EdgeRunner Ventures, which is a small-scale AI and deep tech fund. We have been investing for the past year and a half at the edge of what we call energy compute infrastructure, which is an asset class, a new asset class that comprises a bunch of co-designed AI software, hardware, and then energy generation and storage systems that are used to actually deliver that power at a rate that actually makes sense for people. Now, there's a lot that we're going to be getting into over the course of this entire night, so I'm just going to keep my comments rather brief, but I just want to have a couple, really two principles that I want people to begin thinking about, because this is how, for the past 9 months, I've been traveling to Texas and Canada, and I'm from Texas, so it's not that bad to travel, to Canada, China as well, and I've learned a lot about how different parts of the world are really looking at this problem, and then mustering their primary resources economically in order to rise to the challenge of actually having to satisfy all of these AI workloads that are coming online, not just in terms of magnitude, but in terms of volatility as well. So the first thing that I want to point out, is the first principle, or really first objective function for EdgeRunner Ventures, which is prioritizing the maximization of valuable intelligence per energy unit. And this is subject to having a minimum IQ threshold for the models that you're working with, and then a minimum token throughput as well. These aren't all that useful if they're not really operating very quickly, and they're not all that useful if they're all pretty dumb. But this concept really was on full display when I was in China recently at the World AI Conference, when Professor Wang Yu from Tsinghua University was talking about not just what they're doing at his lab at Tsinghua, but actually really at an entire macroeconomic level, how China has been developing their own AI systems, both software and hardware. And again, these are very tightly co-designed. The way that they're targeting this, and I'll expand the chart in a second there, is not trying to maximize the performance of any one particular chip, but instead setting, or even just trying to get to AGI first. It's a very different goal. What they're trying to do is they're trying to develop the energy systems, the efficient model infrastructure, both hardware and software, in order to achieve a very specific goal, which is getting to the point where you can actually serve GPT-4 or O1 grade intelligence at about 100 token per second throughput, minimum within a 20-watt form factor, at an efficiency rating of about 20 tokens per joule. This is a very, very specific goal that it's not centrally planned or mandated or anything like that, just what the research community and companies have been more or less collaborating towards. And you can see a lot of examples of this with convergence on certain precision standards, DeepSeek and other model developers on FP8, but then also on DeepSeek closely engaging with Huawei, Cambricon, and other chip companies to actually have zero-day support for their models, as opposed to waiting until things get translated from Pluto later on. The challenge with actually hitting this sort of what they call ubiquitous edge intelligence is the fact that almost all GPUs that exist today on a card basis are sitting at still under about 1 token per joule in throughput. This has been the case for quite a long time. I know that NVIDIA has put out charts before about how their tokens per joule have dropped by like 45,000x or something like that. But the truth of the matter is that while the methodology is not really disclosed, they're probably calculating that on a compute-bound basis, when most inference workloads, or most workloads that we care about with AI, are actually memory-bound. And the von Neumann bottleneck of shifting data from the memory chip to the logic chip is what's causing this frustrating ceiling right here for most GPUs. Now, there are some hardware examples that are breaking out of the GPU paradigm, going into ASICs, or even like near data processing or processing in memory, that's pushing you further into this really purple zone here of valuable intelligence in a small form factor that can work on mobile robotics, right? Edge robotics. If you can get that, you have a takeoff here in which you can actually unlock O1 grade intelligence on a form factor that can run pretty much all day with very limited problems. And they already have the infrastructure on robotics to actually be able to support that. Cerebras actually, I'm glad that Asher is here. Cerebras is, I just want to shout out, very, very, very good on a tokens per joule basis. I know it's not like for like because it's a rack scale system, but something like, I don't know, 30, 40,000 tokens per second for like smaller models, and then still getting, breaking past this ceiling, but getting there. But like Cerebras is like, pretty solid, so shout out to them. some of the techniques that we're seeing in China, not as much in the United States yet, in order to try to get around this problem of poor performing chips, are leveraging sparsity and the hardware as an example in order to actually be able to have much more efficient computation. Sparsity is really how like the human brain actually operates, where you're not firing every neuron every time you have to count 2 plus 2. Instead, it's a very small proportion of your neurons that are actively firing at once. That's basically the concept. Chips from a company called Moffat AI, which support up to 32 times native sparsity, are able to actually significantly boost their own tokens per joule throughput from this, like this 0.1 or so frontier all the way up to 2.7, which is a huge jump. Now, the challenge, of course, with sparsity is if you nerf those neurons, are you going to reduce your accuracy? But that's where the brilliance is with the hardware. There's also that, there is no loss in accuracy for them. We're also seeing this in terms of software as well. So in the absence of us actually being able to actually manually model the energetics that go into like what artificial analysis is actually testing out, you can see that in terms of like intelligence versus the cost to actually run the artificial analysis intelligence index, that the latest DeepSeek model is actually best in class. And that comes from actually them migrating away from what was already a huge jump in going from exponential to linear attention scaling with MLA into what they call DeepSeek sparse attention, which ends up taking that linear scaling and then flattening it even further, enabling them to do inference on really long contexts. So lots of really interesting techniques that we're seeing in China to get around these restrictions in terms of hardware, but then also on the software side in order to boost the performance. All of these actually then ladder up into trying to push the frontier of these models that are coming out, all of which are just as smart as American models, into this area over here that actually then allows for being able to put those models onto robots without really a cloud connection, and then allowing for more or less like, I'm going to exaggerate here obviously, but like, sky's the limit in terms of labor productivity. Now, that's on the compute side. So that's like AI, hardware, software, etc. The other side of this energy compute equation obviously is the power. And an issue that I have, living in Silicon Valley but coming from Texas, is that usually the conversation around energy here is more or less with a lowercase e as a subset of oftentimes climate week, honestly. And this is a problem, right? Because in order for us to think about how to solve this physical engineering issue, we cannot come to the table already with an ideological lens that constrains the kinds of solutions that we actually look at. Otherwise, we're going to be locked into a much longer timeline or stuck on solutions that are nice to talk about, but are actually not practical for your goals. I'm going to pick on a couple of here, but solar alone won't get us there. And I know that Eric Brynjolfsson and Elon and many others talk about how we have a star, why don't we just harness it? I would love to see a Dyson sphere in my lifetime as well. But we had an administration actually starting with the Obama administration, but then going into the Biden administration as well, that prioritized solar, storage, and wind into the grid interconnection queue as much as possible, basically cramming as much intermittent renewables into the grid in order to power our ambitions as far as energy go, which from the 1970s to about last year were very flat, right? We didn't really have a lot. I know that it's tempting to say we have a sun, why don't we just harness it? But because of the intermittency with these types of renewables, you need to overspec by a significant amount in order to actually get the reliable base load power to power your AI factories by a factor of like 8 to 10x in some cases. So it's not very capital efficient. Picking on nuclear a little bit, I love nuclear, to be clear. But the question that you need to be asking yourself if you are a startup or if you are potentially investing in a startup is, do you have access to HALEU, right? High assay, low enriched uranium. Where are you getting it from, okay? Up until June of this year, there's only one company on the planet that we know of anyway, that is actually producing at a commercial rate the HALEU that the industry actually needs in order to work for these advanced reactors. And that was 10X, a subsidiary of a state-affiliated company in Russia, which we stopped doing business with after the Ukraine war broke out. So more or less, we're kind of screwed, stuck with a DOE stockpile that wasn't getting any bigger until recently we started to actually produce some HALEU. But is that going to, one, support the build out that we need in the near term? Or two, like, does your startup actually have a pathway to getting access to that? It's going through the DOE. If they're not one of the 10 companies that are currently on the Advanced Reactor program, then open question. I'm going to skip past natural gas here because it ends up being redundant with this. Which is that the objective here that I'm talking about is not to prioritize any one specific kind of energy. It's to minimize the time to power. That's the objective function here. Why do you think that XAI was able to actually go from completely lagging behind the other three major incumbents on this graph anyway, into actually being into second place against OpenAI that had a much longer lead time? That was because by actually, Elon stepped up to the plate and said, okay, we need to build Colossus 1. How are we going to do it? He talked to the grid. He talked to traditional data center developers, and they were all the grid was telling him, no way, Jose, you get 75 megawatts, that's it. The developers that he was talking to were saying, we could get you the power you need in about 18 to 24 months. And he had said, if I do that, I might as well just give up. Why even participate if I'm going to have that kind of a be that far behind? So he worked with a company, Solaris Energy Infrastructure, that already had a lot of small scale, not the large scale, but the small scale 16 and 35 megawatt turbines that he needed in order to get the power up to about what's going to be now 1.1, 1.2 gigawatts of power. They started with just 75 from the grid, scaled up to about 450 in a very rapid timeline, and then now have pretty much doubled. And that is because Solaris is able to get 100 megawatts per month up and running for any of their customers. I challenge you to actually find any other company that can do that today. In addition to that, in order to manage the intense volatility of AI workloads that are jumping 50% every 200 milliseconds or whatever, that's a crazy amount for a single large turbine to actually have to handle. So having a longer portfolio of large turbines and small turbines, along with very tightly co-designed software with the battery energy storage systems from Tesla, allows them to actually be able to gracefully work with these workloads. So wrapping it up, in order to actually think about this in the long run, we can't just be thinking about single maxing any one particular energy source or any one particular chip or any one particular model. The future to actually resolving this problem revolves around co-designing energy compute infrastructure between all the parties in the unified stack. When we talk about the American AI stack, I don't want to see a buffet line where I have to go then pick and choose which ones I want. I want to see a 5-course meal that has been carefully selected by the chef to have absolutely optimal performance for what I actually want. And that's currently where we're at. We have a lot of different entities that aren't really collaborating with one another and that are all trying to get, a cut of the prize. But, we need to be thinking about this in a systems level, in a multidimensional frame. So with that, I'll leave you with those closing thoughts. For more, you can follow my Substack Machine Learning, where I was posting a lot of stuff like this already a couple months ago, and then my Twitter handle is right there as well. I'm sorry, I couldn't read it. So 2 questions then.
All of the solutions I'm hearing about regarding the energy question are where do we get more energy? How do we create more energy? Are you aware of anyone looking at the reverse side of that, which is how do we reduce the power requirement?
Of course. At least within the AI data center context, all of these investments in terms of model sparsity or hardware sparsity, and then other really low-level techniques to try to reduce the number of operations that it takes to really run these models or decode them. These are all things that actually achieve order of magnitude improvements in how much energy any one particular model consumes. So I'm not saying that we keep this side over here, ceteris paribus, and then everything else we gotta maximize. It does require collaboration here, and that collaboration between Solaris and Tesla on their Colossus deployments is one example of that. Any other questions? Yes?
You mentioned HALEU, but I'm curious your thoughts on trisofuel for the SMR.
You say on trisofuel?
Yes.
So uranium isn't the only path in the tech tree to achieving the same kind of reliable baseload nuclear power that we want. There's other technologies like thorium molten salt reactors that are being discussed, But for the most part, the U.S. nuclear energy industry, which again has been pretty much stagnant since the 1970s, the mandate has been basically no new deployments, just keep it stable, keep it stable, was built from an angle of militarization, which then kind of bled into actually energy production. So we're playing catch up now, with kind of taking all of these things that were on the shelf in terms of other technologies like molten salt reactors that China has now then decided, oh, this is perfectly fine for our use case. We're just going to bypass the uranium part of the tech tree. And I would love to see more examples of that so that we get around that particular bottleneck. Because Centrus is only just now arriving to the starting line of providing, at a production scale, the key input that we need.
Awesome, thank you, Ryan. So next we'll have Honor. She's gonna take us all the way back and tell us how to build a data center.
Oh, thank you. Okay, so we're holding up the end here, so I'm gonna bring some energy. I have some copied reports here, bringing it back to the dark ages of, paper. So please don't trip over yourselves trying to get one. Anyway, so yeah, feel free to take one. Won't charge you for them. They are free. Great, thank you so much. Hi everyone, nice to meet you. My name is Honor Masters. I'm a partner at Crucible Capital. So primarily we are a venture fund. We're investing in pre-seed and seed companies in all of the areas that we've already been discussing so far tonight, mostly in and around software. So we want to look for ways to really help financialization, aggregation, virtualization for physical resources, and help sort of smooth those CapEx costs over time as we're basically moving as fast as we can towards this AI infrastructure boom, right? And so why am I up here tonight? We did write a report. It's called Building Data Centers for Dummies. And the reason we called it dummies is obviously, we're taking a joke out of our own playbook, but essentially we've seen a lot of VCs in the space say, hey, we want to invest in data center software, yet they've never been inside of a data center, let alone try to build one themselves. So we thought we would try our hand at doing just that. There are a couple other reasons why. So AirVolta is a portfolio company of ours. They're obviously focused on data center infrastructure management. And so while diligencing that opportunity and many others in our portfolio, we found ourselves building this sort of connected web of hyperscalers, neoclouds, data center owners, data center operators, and we would interview them and ask them, what are the things that you need to see in order to help you succeed? Whether that means managing offtake, as we were discussing earlier, whether that means securing power, whether that means getting interconnection. There are all of these different roadblocks that you face, even just getting to that sort of powered shell phase. So phase one that you're looking at now is really just the bones report, right? So this is getting your land, this is getting your power, this is getting your fiber, this is getting your water. And so essentially, the reason why we fell into this to begin with is because a lot of our LPs, our limited partners, for those that don't know, that invested in our venture fund as well, already had some of this power land and it was already permitted. So they said, hey, investor, you're already looking at this data center space. Do you also know how to help us, monetize this land? And we said, yes, we can definitely take a stab at it. And so we were able to get access to early powered land, one of which is in Maine, Lewiston, Maine. I don't know if anybody knows where that is. But it's a small town. We're building a 20 megawatt site there. 20 megawatts at the end, starting at 10 megawatts. We're also looking at a site that we will build starting at 200 megawatt all the way up to 2.4 gigawatt in Western Virginia. Hard to it's no surprise that we're building in Virginia where everyone else is. But it seemed to us that a lot of these things, every piece of the puzzle, water, for example, folks aren't thinking about the environmental impact on the local communities. There's wastewater issues, there's permitting issues, there's sound and noise issues. I don't know if anyone has spent any time on YouTube recently in the Business Insider interviews, but there's like a really scary dark side of data centers video up there that essentially interviews a lot of the town members and folks that have sort of lived close to Loudoun County in Virginia. We think that this is just the beginning. There are going to be a lot of other issues related to just local impact and folks going to their local politicians and complaining and really just having this sort of NIMBYism kick off. NIMBYism is not in my backyard for those that aren't familiar with it. Then we get to fiber, right? So you have to be on high capacity fiber routes, right? You can't just build it anywhere. You have to, focus on that as well. Otherwise, you're dead in the water immediately. And then obviously power, and a lot of us have been talking about power tonight already, but essentially this is the biggest bottleneck, right? We have to add 150 gigawatts to our existing grid. Our grid is already failing, so what's really fascinating about the fact that our existing grid is currently using only 40% of our asset base, right? We used to be at around 60% in 2001. And so we're having to send more and more kilowatt hours through existing infrastructure, and it's costing everyone a lot already before we've even plugged in a lot of these data centers. And so if you think about it, like even if you take a closer look at your electricity bill today, 10% is going to generation, the rest of it is all crap. It's transmission, it's distribution, it's utility overhead, and you're seeing a lot of frustration with that already for those that are paying attention. We at Crucible really think it's going to be the next hot button issue in politics. We think that eggs were bad. Next, it's going to be our power bills are way too high. They're completely unaffordable. You're already really kind of seeing that come through. I think it's fascinating that a lot of utility CEOs still have their jobs. They're really not managing their risk appropriately. So in any case, we are really investing in tools that alleviate this inefficiency between energy and compute, right? And so one of you, I can't remember who it was, asked earlier, what are we looking at in terms of adding more power to the grid isn't always the answer. How can you squeeze more out of what we already have? One of those is Mercury Compute. They're basically helping utilities with data centers essentially get more out of their flexible assets. So whether that means creating a market-making mechanism between utility and AI data user, whether that means working with the data center owners themselves, they want to increase capacity, increase utilization, so they're helping really sort that equation out. We're also working with a company called Double Zero. They are aggregating dark fiber, so basically building a low latency network. There are a lot of undersea cables that are very much underutilized, so they're building something that's going to help tap into those resources. You're sort of seeing a theme here. We're trying to invest in things that are helping sort of squeeze more out of what we already have. We also have Orn AI. They're actually here, Cushman Wayne are over there if you want to go chat to them. But they're really building a trading platform for compute. So basically just increasing GPU capacity by creating a market-making mechanism, really just selling really to the financial partners in this equation, right? Because a lot of them, like you're seeing private credit get super involved in this space. And so they're looking for ways to offtake some of that risk, right? So anyway, we are really excited about this space. We think data centers are the new refineries. A lot of us came from the oil and gas background. We think that this is a huge opportunity to invest in sort of software tools that are enabling this transition. Couple asks before you take some free reports. We do have, obviously, these 2 sites. We're looking for a few tenants as well for both of the sites. We're also looking for a couple of operators as well as folks that are going to help develop the sites. We've been interviewing a few of them. And then lastly, if you're building a company that sort of suits this bill and you're excited about the space or you literally just have an idea on the back of a napkin, we back founders at the earliest stages, $500K to $1.5 million checks, so happy to chat anytime. And that's it.
2 questions?
Yeah. Stunned everyone. Nice.
Yeah.
Sorry I didn't have slides. I found out about this yesterday.
How do you think about data center pedagogy in general? Do you feel like there aren't resources like the one that you created, just lacking at a splash?
Not in VC land. I think that there's a real gap for sort of knowledge around basic concepts like PUE and just utilization. What does capacity mean? I do think that there was sort of a thirst in the market for something as basic as just how we build a powered shell. We're going to have a part 2. Certainly it's going to be out on Twitter digitally, so we're going to distribute that as well. But that will be about the GPU procurement, the cooling, the networking, everything that goes on inside the guts inside the data center. So we do think that there was a lack of knowledge in the space. Sure. Yeah.
To kind of build onto that, do you see the data centers for AI as more of a natural resources type play compared to like more to a traditional data center would be like not quite the same thing, right? Where you're selling differently than you would with natural resource.
Yeah, we definitely, I mean, the analogy I was building on before was that we think data centers are the new refineries, and compute is essentially, the oil, and we're going to commoditize the entire value chain from start to finish. So yeah, I do think it's a natural resource. And there are a lot of ways that it even trades in the same way that natural resources would, oil itself, and also Bitcoin, which is interesting as well. Yeah.
What do you,
Oh, sorry.
Okay, thank you, Honor. So next we have Xander. He's going to talk more about the land aspect of things and building Kratos. And we only have 2 speakers left, so I know we're almost at the end. And afterwards, we'll have pizza for everyone, and we have water over there, so yeah.
Awesome. Hey everybody. I didn't expect to be barefoot for this, so forgive my nervousness. So everybody, I'm Xander. I'm co-founder and CEO of Kratos. We started Kratos about 6 months ago on the premise that there's been some reports floating around that 15 to 20% of the U.S. grid is not utilized at any given time. For perspective, that's about all of Texas and California's energy needs at any moment that's not being utilized. And the main reason is that we have to size the grid for peak, right? So Evan was talking about this earlier in a different construct, but we have to size the grid for the coldest day in January or the hottest day in August, which only happen a couple times a year, right? So that means we just have this massive amount of energy. Some estimates show like 200 gigawatts of available capacity. Now, the problem is that it's not in neat little 1 gigawatt chunks right near major metros, right? It's spread out all over the US in 5, 20, or maybe 200 megawatt increments. And so the question is, how do we make use of that power that's already there? And that's what we're working on at Kratos. So we call local utilities to figure out where the power is going to be. This is kind of a fun exercise, working through the phone tree and trying to figure out the electrical engineer who knows what's going on in the local grid. We run system impact studies to validate what the grid can actually produce and what it can transmit safely. We work with landowners to structure sites and options. We rezone and secure entitlements. We bring local communities on board, and then hopefully we can sell or kind of joint venture these assets with large data center developers, Bitcoin miners, or chip designers. And so the goal here is really simple, which is harness existing electricity to make it easy for operators, capital partners, to build data centers faster, especially in this range of like 50 to 250 megawatts, where the opportunity is pretty wide open in terms of grid availability. So for example, one of our most recent projects is in Indiana. They have a significant amount of power available, over 500 megawatts. A hyperscaler was interested, but the project stalled due to a federal lawsuit and local pushback. A new mayor was elected who is skeptical of data center developments, and understandably so. But this is exactly the kind of situation where I think the hard work matters and can move the needle. So we are stepping in to kind of re-educate the community. We've built some economic development estimates. We're meeting with the mayor next week and trying to get folks aligned so that development can restart on the right footing. And so this example shows, I think there's some shortage of power if you're looking for like a gigawatt, but if you're looking for a smaller increment, say 500 to 200 megawatts, that's probably available somewhere on the US grid today. You just need to know where to look. You need to be willing to put in the work to get the local community on board, get the entitlements done, get the land deal sorted with the local owners, and get all these things put together. So I think in short, if we can unlock even a fraction of that 15% of the US grid that's available today, we can build hundreds of flexible mid-scale AI data centers in months, not years, which will keep utilities, grids stabilized because the loads are a little smaller, a little easier to handle. And it will also share some of the economic development benefits across a bunch of local communities that, frankly, don't really know what AI is, and we should probably help them understand. So that's it. Thanks, y'all.
Oh, wait, 2 questions, sorry.
Hey, so who are the end user of these size data centers? Like, are they the hyperscalers, or is it maybe like a CoreWeave or something like that?
I talked to the land folks at one hyperscaler, and they politely told me they don't get out of bed for less than 300 megawatts. So I think it's a mix of mid-market data center developers. So these are sort of edge compute type folks. Usually it's been traditional compute, but it's branching into AI inference. It's chip designers. It's some AI model labs that need sort of development facilities for R&D purposes. And also Bitcoin miners are particularly interested, especially in the rural sites, because they don't have like an inference timing problem. Yeah.
So with respect to like the community advocacy that you guys are doing, there's definitely seems to be sort of a social contagion around the town banding together to fight off big business. It's basically any classic Western plot. But in your experience with these communities and the mayors, what are some of the talking points or some of the conversations that you're having that are illuminating the problems that they care the most about, and how are you mitigating those?
Yeah, I think the first step is understanding what do they care about from an economic development perspective. Oftentimes it's like raw number of jobs. If that's the case, like we're probably not going to be a fit, right? Because data centers just don't provide as many jobs as, say, a manufacturing plant would. I have successfully convinced a couple of folks that, like, well, let's look at long-term manufacturing. Like, do we think people are going to do that, or do we think like Tesla's Optimus robot are going to do that? Like, let's be realistic about where this is going. Do you want to reserve 100% of your available capacity? Which, you know, by the way, some big industrial parks sit developed and vacant for decades, waiting for like a manufacturing plant to come in when they could be using those resources that power the utility for a data center that will provide immediate economic development benefits in terms of property taxes, sales taxes, local jobs, all that kind of stuff. So it's a little bit of a sales discovery effort, but I'm sort of just trying to point them in the right direction of what do you care about? Here's what we have to offer. Do you want it or not? Because there's communities all over the US that do.
Okay, but last but not least, we have Marilyn from Vantage. So she's going to tell us how is this all financed on building it.
Hey guys, we're gonna keep this quick because Honor kind of hit most of the basic things in terms of the build out. So this is mostly just on kind of like market size as well as financing. Okay, data center financing. All right. So as the global data center industry continues to experience a double-digit growth, in 2025, the development financing is set to hit another record year with total capex, so capital expenditures excluding IT, expected to hit 1.7 trillion by 2030, which is a huge amount of capex. And there are not that many capital providers, and we've discussed some of the capital providers that can fund this type of build out, but there are only really a handful. And this is why a lot of capital providers have actually kind of consolidated into their big data center platforms. So you mentioned, for example, Blackstone has QTS, that is their kind of main data center platform. Vantage is funded by Silver Lake as well as Digital Bridge. And these companies have kind of scooped up some smaller data center providers as well. So this reflects quite a bit of kind of digitization among the US as well as kind of economies worldwide. So within the United States, the data center market is projected to reach roughly $250 billion by 2030. From a power perspective, the U.S. data center electricity market is expected to grow to $15.2 billion in 2025 and to $21 billion by 2030. This is a CAGR of about 6.6%. And then nationally available, the megawatt supply is about 8.2 gigawatts right now, which there is quite a bit more demand, and so we are kind of also racing to meet that. In terms of the data center business model and build costs, so if we think about the kind of data center business model, we are really kind of building on infrastructure in a kind of typical fashion. The potential ways to kind of decrease costs as well as increase the speed of deployment are basically modularity, as well as kind of this rapid deployment model of building more of these data center components elsewhere versus having to do them all through the kind of construction model. In terms of, and then also of course the vertical integration of energy supply. So this has been a discussion in Vantage that basically there is a thesis that those kind of the companies that are most able to vertically integrate are those that provide energy, and so they can kind of learn to build data centers, whereas it's a little bit harder to kind of learn to build energy. In terms of customer focus, Vantage specifically focuses on the hyperscaler market, as well as some next-gen AI, although there are some kind of holdbacks with the next-gen AI companies because they are not exactly credit-worthy off-takers, and so that is something that has to be backstopped by other kind of more credit-worthy customers. Retail and edge is something that kind of is a different sector of market, sort of. And so the REIT structure is a pretty common structure for data centers in the US. This enables a lot of tax efficiencies, but then sometimes requires longer holding periods up to kind of 2 years after first receiving revenue. Construction costs, they average about 11.7 million per kilowatt. And they range based on kind of the market as well as just other types of density and liquid cooling and everything kind of involved in making these data centers. And so in terms of modular data centers, there is a 10 to 20% cost savings and faster delivery. In terms of debt financing structures, so as the data center is kind of being built out, the construction loan is used to kind of finance that portion, similar to kind of project finance. So the loan to cost when backed by credit-worthy leases, you would sign the leases first and then get the construction loans based on those leases, with the debt sizing being 70 to 80% of the LTC. The term loans are put in place once the construction is finished, and so debt sizing for that is a debt service coverage ratio covenant of 1.25 times NOI. And then we're looking at debt pricing, and I believe that this debt pricing is a little bit more so for public development companies. So that would be like your Digital Realties of the world, your Equinixes, because the debt pricing does go up the more kind of capitalized these companies become, and the private companies are able to take on more debt. Securitization is another version of debt financing, and so you use asset-backed securities as well as mortgage-backed securities for liquidity, portfolio funding, and refinancing. And then typically these will be syndicated once they get to the kind of large deals, so over $1 billion. Vantage, for example, recently raised, I believe, $40 billion for their deals in various US locations. In terms of equity financing, there are certain investors that invest in the development assets versus the stabilized assets. This mostly hinges on the kind of IRR criteria. So you're looking at these technology private equity firms as well as real estate development firms, infra firms, and sovereign wealth funds. that are looking at 20 to 25% IRR targets, and sometimes they can far exceed that. However, one of the kind of major risks with the development is the build-out timeline, and that significantly affects IRR. So the stabilized yield assets, we're looking at sovereign wealth funds, pension funds, infra funds, and REITs. They're looking for more like a 10 to 12% IRR target, but they also aim for pre-leasing risk. So valuation, we are looking at cap rates for data centers around the 6 to 6.25% mark, but these are very dependent on transaction structure as well. In terms of data center financing risks, there are several for the investors, both the debt and equity investors. Customer credit is a big one, and this is something that we have had to deal with as we see these kind of neo-cloud type of businesses that don't necessarily have kind of the credit worthiness profile that we're looking for. They do have to be kind of supported by the Oracles and Microsofts of the world. In terms of construction, there are delays and cost overruns, of course, but this is sometimes mitigated by something like more modular building. Technology change is of course a big one because you're dealing with kind of long timeline infrastructure and really heavy CapEx needs where technology could kind of change and become obsolete. And so you're also looking at, of course, regulatory environment, and then also just kind of, I think we're dealing with this quite a bit right now, is basically, are we forecasting demand correctly? And I think that that's a major question. And then, of course, the power supply, which we've all spoken towards. And that is all we have. And so, any questions?
We have two questions, Tim.
On the creditworthiness side for your customers, there's oftentimes a disconnect between, say, what creditworthiness looks like in public capital markets versus like private here in Silicon Valley. So for neoclouds or large research labs that haven't yet actually raised debt, so they don't really have a credit rating, how do you guys think about what is the baseline for creditworthiness when engaging with the customer?
So I think that we basically look, because we are backed by pretty established private equity firms, they're definitely looking for creditworthiness profile, and so that really comes into play when there are either joint ventures or something involving basically these more startup type of companies, but with basically financial backing from something like NVIDIA, and that is how most of that ends up getting done. On our side.
Hi, can you talk about a little more about the largest pain points for you right now when you raise capital?
Yeah, so in terms of raising capital, I think one of the larger pain points is actually that we have a lot of interested parties in basically the development of these assets, and I think that that is all well and good, but I think that that is underwritten with the expectation that these assets will be sold at the stabilized rate, and as that stabilized rate entails probably more risk than something like a bond or other types of kind of yielding assets, you basically run into this issue of there are not enough buyers to kind of pick up more of the stabilized type of build out versus you have a lot of interested parties in the development.
So, what you said then, you have a lot of interested parties in the what?
In the development.
In the development. So many in the development, but less on the refinancing of the
Right.
Okay, so that was all of our speakers. Firstly, huge thanks to Jeremy and ABI House for hosting us. So I think we heard from a lot of folks today. We're going to have pizza, so make your way there in a couple minutes. I just want to talk a little bit quickly about why we're all here today in this beautiful house. This has been a huge build out. Everyone's been talking about it, but actually being involved and actually doing the labor of building out a data center, how to build out a data center for dummies is very different than talking about building gigawatt sites. You have folks like us, AirVolta, doing like the infrastructure management, SF Compute, Cerebras, chip management. I think it's awesome to bring together all the folks working on all the aspects. I know there's lots of folks in the audience working in power. I know Some Energy, a lot of Giga Energy is here. There's folks on the software side and the compute market. So definitely get to talk to everyone here. It's not just the speakers. And we're all building in the space, so it's super, super exciting. Thank you.
Jeremy, I don't want to break your phone. No, thank you.
Thank you. This was
Yeah.
really great.
How are you?